talk will be by Dr. Mohammad Nurujjaman from TIFR Center, Bangalore. Effect of observation time in data assimilation by means of synchronization for Chua oscillator.
So, good morning. The title is already told, effect of observation time in data assimilation by means of synchronization. In the morning we heard the Didier talk that nudging, basically same techniques. So this work is a part of work we are doing with this group, Punit Parmananda from IIT Mumbai. So this kind of work is done by Kalne group, S.C. Young et al. And they published this that work in this journal, and they used Lorentz equation. In our case, we use Chua model, and I will describe Chua model a little bit. Then what is synchronization, then some results, and finally conclusion. So this is the circuit which is used for chaos study by Chua, where this part is nonlinear, which is giving all these nonlinear things inside this circuit, and the three variables, the voltage across this C1 capacitor and voltage across C2 and current in this inductor is forming the variables, and if we use Kirchhoff's law and non-dimensionalize, then we will get these three set of equations, where the G is the only term, it includes nonlinearity, and through which system shows different nonlinear behavior. So to do synchronization or our experiment, we have used chaotic regime, and if we solve these equations for different parametric regime, we will get three kind of attractor. One is the outer one, which is basically divergence. That is not inside the desired regime, and the two is inside. So if we zoom the middle one, we will get two attractor, which is two fixed points. So these are the typical chaotic time series for Chua circuit, and in this case, this is the output of our model value. So now, okay, so this is the regime where we are working. Now let's see, if we run the Chua model with initial condition which is little bit perturbed. So this is the x component of Chua model. So initially they are same, but with time we see that in this time they completely lost each other. So there is no follow of one time series with other. So this is called exponential divergence. So in chaotic circuit or in chaotic system, we get this thing, and this exponential divergence can be quantified using Lyapunov exponent. Here for Chua model, we got Lyapunov exponent 4 per millisecond. Here, so this, so okay, we have three variables x, y, z. So I am plotting there basically x component, x component of those three variables, or x just. So if we find Lyapunov exponent will get 4, and then the Lyapunov time will be 2.5 into this, and this will be second. This is for no, the Lyapunov exponent. Or this. So this is two different initial condition. They are very close. So initially they are following each other, but after some time they diverge completely. So the idea is that how we will force the system so that they will not diverge from each other. So the idea is synchronization. So this was first given by Pecora and Carroll in this paper, and the idea is that if we add feedback, so with each term, or even for one variable, what will happen? They will synchronize with each other. In our case, we have taken two initial conditions, which I have shown here at two different points, and after some time, with k equal to 1.2, we got complete synchronization. Now, so this is the synchronization. Now, how we will use this as a data assimilation, which is basically nudging. So the idea is that if so we have two systems here. One is red, another one is black, and they are following each other. So if we have observations, and that defines my trajectory, and now if I can force the system to follow my observation, so that will be basically the idea of data assimilation. So in terms of synchronization, we can tell that data assimilation is a master-slave synchronization, where master system is my observation and slave is the model. So in this work, what we have done, we are trying to find the effect of the observation time on this synchronization. So what we did, we have a free model run from where we made an observation vector, and we did it by taking some time step. For first case, we take this time step 2 into 10 raised to minus 5, and we know our Lyapunov is 2.5 into 10 raised to minus 4 seconds. And if we subsample our trajectory to get observation using this 4 time, and if we do same experiment, that is synchronization experiment, and if we plot RMS error versus coupling constant, the constant which is responsible for to synchronize my system to observation, then what we got, for 2 into 10 raised to minus 5 seconds, for this data, when we have taken in this interval, we get a perfect synchronization regime. So this is my region for coupling constant, where we have got synchronization. But when we have increased the observation time, what we got, the RMS error is increasing. So that is the RMS error for X, Y, Z, and this is the for X, Y, Z, all three. And this one is the synchronization, RMS error for synchronization of this time step, that is 5 into 10 raised to minus 5. and then this one is 7 into 10 raised to minus 5, and the final one where we don't have any synchronization, that is 1 is to 10 raised to minus 4. Now let's see the time series. So that is for we get perfect synchronization, that is the model is following observation when our time step is 2 into 10 raised to minus 5. But when the time is 5 into 10 raised to minus 5, that is almost 4 times less than Lyapunov time, then we see that model is diverging from observations. And when we increase time step further, what we got, these are the black lines are observations, and this is the model. So for higher time step, system is diverging. So, and these are the results when we have coupled x component only. And we got similar result for when we coupled y component to the system, but we got synchronization regime, but little bit shifted. When we coupled when we coupled z component, we did not get any synchronization. So z component observation is not our observable, we can tell. Now, so these are the results without noise. Now if we add noise with observation, then what will happen? Then what we have got, when we coupled x component only and did the same experiment, we found with increase in noise level, the RMS error is increasing, but not the pattern, but the pattern remains almost same. So so we can conclude or not conclude, or we can infer something that in case of synchronization, noise is not that much destructive when we got synchronization. So the idea is that where we have added noise, when we have synchronization, but that is when our observation step was 2 into 10 raised to minus 5, in which case we got full synchronization. At that time we added noise, and we repeated the experiments with different noise levels, and we got this thing. So from this figure we can tell that the noise is not desynchronizing the system, but it is just perturbing around that trajectory. So these are the typical trajectory with noise. The black one is the without noise, and there is another one, red one, which is 10% noise, and the blue one is with 40% noise level. So so these are the result we got with different time steps. So we can tell that though people are telling there is no relation with Lyapunov time and observation time, but at least here we have got at least that the observation time should be less than Lyapunov time, and these kind of techniques will be useful for data assimilation where observations are frequent. And number 3, this will be also useful if our observation vector is small. And thank you.
Your nudging matrix is diagonal, right?
My nudging matrix is K. So
so that's diagonal, right? So is that a necessary part of the synchronization strategy that you're nudging?
Yeah?
Is
Sorry?
that a necessary part of the synchronization strategy that your nudging matrix is diagonal? Or could this work with non-diagonal matrices?
So in this case, we have used just the diagonal. So what is that actually? That should work, but we have not tried. Yeah, that's it.
X ups that you used here.
Oh, so the X orbs is basically one model run. So we have a free model run with some different initial condition. Now we have collected observation from that trajectory with different time step. So in this case, where we are getting synchronization, the observation are these points, this red dot. This case, for this time step, these are the observation. So for this time step, we are not getting synchronization very well.
Suppose you nudge only one variable.
Yeah, that we have done.
Which one?
The X variable only. So these are the results using X variable. X variable, then this one is Y variable. But when we have just nudged Z, we have not got anything. So